This is problem 3 from exam 2 from spring 2018. As I mentioned in the overview, this is probably the first problem I would do on this exam. It asks us to test whether the Clausius-Clapeyron equation would be a good model for steam in the vicinity of 100 degrees C. So the values are given over here. I think this probably got lost in the sort of archiving of the problem, but it doesn't actually report units here, at least not for everything. So I'm going to write that in, and I hope the students at the time had it. I don't remember it being an issue. But the enthalpy is in kilojoules per kilogram of water, and the specific volume is centimeter cubed per gram. So this is centimeter cubed per gram. Of course, we would expect, you should expect your professors to tell you the units of data when they give it to you. And pressure is in kilopascal, temperature is in Kelvin. And I think that's all you need for this problem. So the Clausius-Clapeyron equation, there's a few different forms of it, but the form that I will use is I'm sorry, I'm having a little trouble with my Okay, the form that I would use is dln psat d1 over t. And remember that students will have equation sheets that will tell them these equations. So delta H of evaporation over R. We have to get the right units for R. If we're talking about pressure in kilopascals, temperature in Kelvin, and delta H in kilojoules per kilogram, the value of R that I looked up, again, I would expect R to be provided in the correct units. I don't really believe in writing exams in which obnoxious unit conversions are bogging you down. But the value of R that I have is 8.314 times 10 to the minus 3 meters cubed times kilopascals times Kelvin times mole. And since we're working with water, these are steam tables, we need to convert 1 mole of water is 18 grams. And then we need to convert 1,000 grams per kilogram. And that should give us the correct units for R, and this comes out to 0.4619. Okay, I'll make a little table for the values that I would want to test the Clapeyron equation in the vicinity of 100 degrees C. So temperature, 100 degrees C. We're also going to want 1 over T in Kelvin, so that's 1 over 373, which is 273 plus 100 is 0.00268. By the way, you often have to carry a lot of digits to get accurate answers, and I wouldn't worry too much about that. It's similar to units. As long as you show us the right procedure, we're not going to grade you too harshly if your numbers are not very accurate. So the delta H from the table, which is here, delta H of evaporation is 2256.9 kilojoules per kilogram. And we also want the PSAT in kilopascal. That is 101.33 kPa, and we can take the log of it. It's going to give us 4.618. Okay, since we're interested in a derivative, right, we want a derivative, we're going to approximate it as a delta ln psat over delta 1 over t. And the next row in the table is 102 Kelvin. So I'm going to have 102 degrees C and 1 over 375 is equal to 0.00267. That makes me think that's not very accurate. But have no fear, I did these calculations in Mathematica and carried lots of digits that I'm not showing here. Obviously, you wouldn't be able to do that on an exam, but remember, it's about the process. Okay, so we have an ln psat, we have a 1 over t, and we can look at the derivatives. We have them at two temperatures and multiply by negative r. So delta H evap is going to be approximately equal to minus r, minus 0.4619, times the change in the ln psat, 4.689 minus 4.618, divided by 0.00267 minus 0.00268. And this comes out to 2293.6 kilojoules per kilogram. I did grab the correct answer, and I think they're pretty close. So I would say this is approximately equal to 2256.9, which is the tabulated value. So I think that's actually pretty good. Another way to, so I would actually just write something like seems close or reasonable. Boy, I don't know how to spell the word close. Another way to approach this problem that I think is kind of equally valid is to go back to the basic assumption and test whether that is true. So if the assumption is true, then the equation should be accurate. And the assumption behind Clausius-Clapeyron is that Z of the vapor, the compressibility of the vapor, is approximately equal to 1. In other words, it's an ideal gas. And that it's much greater than the Z of the liquid. And remember that Z is PV over RT, and we're comparing things at a given temperature and pressure. So really what you can do is compare the molar volumes. So the V of the vapor from the table is 1673. Again, that is this number. So 1673 centimeters cubed per gram, but the units are the same. For the liquid, it's 1.044. Okay, so definitely V of the vapor is much greater than V of the liquid. So it's 1,000 times, or 1,600 times, in fact, greater. And that seems like a good assumption. And that also means, by the way, since Z is proportional to V, Z of the vapor is going to be much greater than Z of the liquid by the same proportionality. Now we should test whether Z of the vapor is going to be approximately equal to 1. So that's PV over RT. And this is going to be, the pressure is 101.33 kilopascals. And then our volume is 1.673 meters cubed per kilogram. I know I'm skipping steps, but that's how you convert from 1673, what was that unit again? Centimeters cubed per gram to meters cubed per kilogram. and R is 0.4619. The units are meters cubed, kilopascals over Kelvin kilogram. Kilograms cancel, meter cubed cancel, kilopascal, and then we need temperature, 373.15. I don't know why I suddenly added the 0.15, but that is correct. And so this comes out to 0.984, which I would say is pretty close to 1. So the assumption behind Clausius-Clapeyron comes out well, and I don't know if you have to answer the question both ways. In fact, I would give full credit for either approach. But we're showing that not only is the Clausius-Clapeyron equation pretty accurate, its underlying assumption is pretty accurate.